based on. Good that people are coming from. It's Paul André Mellies from TPS, the Kiepenpreuve system. Are you a computer scientist?
Oh yes.
Yeah, he's a computer scientist.
Yeah.
It's good to have one of those.
Yes, so Bob mentioned a bit earlier that computer scientists are obsessed with taking small parts of the global phenomenon in order to analyze it and axiomatize it. So I will really do this during this talk. I will be interested mainly in negation. Okay? And negation is a topic that logicians are interested in. And so I will explain that just looking at negation and nothing but negation is interesting and connected to some problems and techniques that were mentioned a bit earlier too during this talk by Bruce about cobordism. And the main, if you have to remember one thing from this talk is the fact that logic has to do with cobordism. And it's not a fact that I discovered myself. In fact, it was noticed by Brian Day and Ross Street. And I think it's important to advertise it. So mainly this talk will be about this idea and a relaxation of it related to game semantics. Okay? And game semantics is an important topic in logic, and it may be seen as some kind of relaxation of the usual cobordism. Okay? And I will explain a bit all of this. So, okay, so that's the beginning of this talk. Okay, is there some kind of relationship between proofs and nuts? Okay, and I will define here the idea that, in fact, it's possible to develop an algebra of proofs in the same way as there exists an algebra of nuts. And this algebra of proofs is something known in the circle of logicians, and it's called categorical semantics of proofs. And so I will explain the relationship. And the starting point is really game semantics. And the idea of game semantics is that every formula initiates a game, a dialogue game, where every proof produces a strategy able to convince the opponent that the formula is right. And every counter-proof produces a counter-strategy trying to defeat and to refute the formula. And if one thinks about logic from this interactive point of view, then negation, if you like, or duality, is not about transforming the truth into the false, okay, and the false into the true. So it's not an action really on the Boolean algebra. It's an action on the players themselves. So negation has to do with reversing the point of view on the interaction. So typically, when proponent plays the game A, opponent plays the game not A. And negation amounts to reversing the board. Okay? And there is a brief history of games and categories. And it started really in 1977 by a work by Joyal, who produced a category of Conway games. And then linear logic came, and a lot of work was devoted to understanding how to produce a game semantics of linear logic that would be integrated in the categorical approach to proofs and programs developed in denotational semantics. So typically, Blas produced the semantics of linear logic, but it's difficult to express it, to organize it in categories. And so, well, there is a lot of work planned to clarify, to understand the categorical meaning of games. And Samson is an important part of the story here. And my question as a practitioner of game semantics was to understand how it's connected to string diagrams. So you've seen already string diagrams introduced in Bruce's talk. And the idea is that if game semantics is an account of logic, so if game semantics can be expressed as string diagrams, then it's a connection to physics and to other parts of algebra. That was really the motivation behind this work. And the first thing to say is that one should start from something, and the thing has been produced by Jim Lambeck. It's a very nice relationship between proofs and categories. And the idea is this one, that consider the notion of Cartesian closed category. So it's a category with a Cartesian product and an arrow. And the main bijection says that A times B, so a map from A times B to C, is the same thing essentially as a map from A to B over C. And it may be represented in some bicategory of profunctors or modules in this way. Okay? If you like, the times is between A and B is transported to an arrow on the right. Okay, these string diagrams. And okay, now let's construct the free such Cartesian closed category. Well, its objects are formulas and its morphisms are lambda terms, so terms of the lambda calculus, up to some notion of syntactical symbolic conversion. So here is very quickly what the lambda calculus is and its types. Okay, so it's very symbolic, it's very syntactic. And from this follows the wrong impression that proof theory is inherently syntactical. But what we should remember is really the idea behind the notion of free Cartesian closed category. It is that whenever one has a functor from C to D, and D is Cartesian closed, the functor may be lifted to a Cartesian closed functor, if you like, between the free Cartesian closed category of C to D. And this functor produces invariance of proofs. Okay? So whenever you have a proof, you look at the image of the proof. So the proof is a morphism in the free Cartesian closed category. You look at its image, and this image is invariant, is an invariant up to symbolic conversion of the proof. Okay? So from that point of view, it's very similar to what people do in knot theory, because what they would do is not look at the free Cartesian closed category, but the free ribbon category, okay, or the free tortile category. So you should think of a tortile category as a monoidal category with these generators here, and these generators are, in fact, the generators of knots, okay, in a two-dimensional kind of algebra. And the two-dimensional kind of algebra is produced precisely by monoidal categories. Okay? So here are the generators, and you have then the relations between them, which are formulated as coherence diagrams in the tortile category. But the point here is that the free tortile category is a category whose morphisms are, well, frame tangles. Well, you should think of them as kind of knots, open knots. Okay, so they are categories of knots, and then the same diagram as before, in the case of proof theory, enables to construct knot invariance. Okay, the idea is that whenever you have a functor from C to D, and D is a tortile category, then you may lift the functor to a tortile functor. And it's a way to understand. And to establish that the typical polynomial invariants of knots are indeed invariants up to deformation of the knots. Okay? So typically you will produce a category D whose morphisms are such polynomials, and prove that it is a tortile category. And once you've done that, the general pattern here tells that they produce, the morphisms of this category D produces indeed topological invariance of your knots. Okay? So you see there is here this picture in the lambda calculus and semantics of proofs and programs, and here the same picture exactly appears in the case of knots theory. The point is that in the first case it's really symbolic, whereas in the second case it is well, topological at the same time, okay? Because it has to do with knots. So the question is it possible to have a kind of topological notation for proofs, so that proofs would look like knots? And the intuition is that game semantics is inherently about this, because the intuition of game semantics is you don't describe a proof as a symbolic object, but rather as some kind of strategy, but this strategy, as we will see, is very naturally written down using string diagrams. Okay? So the main idea here is let's describe proofs using string diagrams, and in fact, in a way, we know already how to do this because this is the purpose of game semantics, and game semantics is a long topic. Okay. So it's really about connecting these various fields and capture everything in a single framework. So let's call dialogue category a category equipped with a negation. So a negation is a functor, okay, which is contravariant. Because the idea is that when you have a proof that A implies B, but the proof is described as a morphism in your category of proofs, and the morphism is here, then you will get a proof that not B implies not A, and the proof will just be the negation of it. Okay? And this is, does this work? This is why there is an up. It says that the functor is contravariant. Okay? And so, yes. So a star autonomous is this plus the hypothesis that the double negation of a formula is the same thing as a formula. Okay, it's isomorphic. Okay, so the whole point is let's remove this hypothesis. So let's remove the hypothesis that negation is involutive, and let's carry on.
When you remove the hypothesis that not A comes back to A,
yes.
do you not also often anyway remove the equivalence of the contrapositive that you've got on the blackboard? In other words, it's no longer necessarily the case that not B implies not A.
So what we will see is that we have this, okay, but this is not necessarily an isomorphism, okay, and it is a very common situation, okay. So typically, if you start from a monoid, or let's say symmetric or braided monoidal closed category, okay, every object induces a negation, and the negation of A will just be defined as A. Okay. And indeed, it's a star autonomous category when the bottom has the selected object here has the dualizing property that this is an isomorphism. I mean, the canonical morphism. But I will carry on, okay? Because I will come back to this point later on. So the important thing here is that it's possible to describe the free such category, and of course, just like usually in proof theory, it's a category whose objects are formulas and whose morphisms are proofs. Okay? But at the same time, it's possible to think of it as a category whose objects are games and whose morphisms are strategies. Okay? And these strategies are total strategies and innocent strategies. So there are usual notions in game semantics. And as we will see, this topological way of describing knots is very naturally expressed in three-dimensional string diagrams. So like surface diagrams, if you like. And what this says is that game semantics is not really semantics, if you like, of something that exists before. It's rather a direct description, using string diagrams, of a categorical situation. And the categorical situation is quite simple and natural.
Clarifying
Sorry.
question?
Yes, yes.
It's just a clarifying question. If you've got a morphism from A to A, that's presumably a strategy for playing A.
Yes.
But if you've got a morphism from A to B,
Yes.
that's a strategy for playing both at once in the Conte style, or what? I mean, what does it mean?
So, yes. So a strategy from A to B will be a strategy which will play the two boards at the same time, okay? And maybe it will grasp some information from his opponent on A to plane B, and vice versa. So a typical example is the identity morphism, because it plays in A, and what it does mainly is transmit the information from one player to the other. Okay? So, so what I will try to do now is to present proofs by generators and relations, just in the way people would do in algebra. Okay? So typically, the tortile categories before, they are also presented algebra. They have an algebraic presentation with these braidings and dualities. So we'll do the same with proofs. And of course, the difficult thing is to give some kind of good algebraic reason behind the generators and the relations between these generators. Okay. So the first observation, which is a very basic one, is that every negation defines a pair of adjoint functors. And the reason is here that a proof from A to not B, okay, is the same as a proof that A tensor B, okay, cannot hold together, which is a proof that A tensor B implies not of 1, okay, the negation of the unit. And so it's completely symmetric. So then this is the same. The proof from A to not B is the same as the proof from B to not A, and this may be seen as a map from not A to B in CR. So you see, there is an adjunction here. Okay, but negation is adjoint to itself.
So L and R are both the negation.
Yes. So if you think about it interactively, so and here comes logic. Negation, the L negation is about giving my turn, and the R negation is about getting your turn. Okay. So they are not the same negation in a way. Okay, but at the same time they are the same up to the duality between a category and its opposite category. Okay. So you see, what is very interesting algebraically is that there are two dualities coming in, the logical duality, if you like, and the duality between a category and its opposite category. And this duality between a category and its opposite category is something very apparent in the bicategory of modules, if you like, because then it's really a duality in the usual sense, okay, in the algebraic sense. So, anyway, so there is an adjunction, and from this we can say, okay, since there is an adjunction, I may use the formal theory of adjunctions and the string diagrams. All these things develop on Ross Street. And so what this means is that an adjunction may be presented. So the two generators of an adjunction are the unit and the co-unit of the adjunction. And so if you want to read the diagram, this here means this, okay? This is R applied to L. So in a way you should read maybe in this direction here. And so the identity, so there is a natural transformation, eta, from the identity functor to the monad here. Okay, so this is the unit. And there is a co-unit. And they're the same up to the duality. And here the blue color, just like in Bruce's talk, the blue color is the category C, and the red color is the category red. Sorry. The red color is the category Theop, it is dual. So if you like, you could think of it as the universe of the player, and this is the universe of the opponent. And the nice thing is that, as we will see, game semantics is about the frontier between your turn and his turn. So, one way to think about, the functors are like moves, okay? So this is a game where opponent plays a move and then player answers. And the strategy consists just in answering immediately as soon as you get the opponent move. Okay? So this says that, the functors are moves, and the natural transformations are strategies. So a typical proof, okay, will give rise to a typical natural transformation. It looks like this. Okay? And in game semantics, this says, well, there is some opponent move here, and I will answer. So the strategy will answer this move. And then opponent plays again, and then the strategy plays here. And then the opponent plays here, and then, okay. So it goes a bit like this. And you see here, the strategy here plays the two games in parallel. So it's a map from RL to the power 3 to RL to the power 2. Okay? So, okay, and now, imagine you have three such natural transformations or strategies, and you want to put them together. Then the intuitive thing will be to say, okay, this thing just amounts to one move by opponent, and then the answer here. So the question is, what does enable this topological deformation of this composite here into this simple unit here? Well, they are precisely the two-dimensional relations, so the triangular laws of adjunctions. And the triangular laws, they are just saying that you may deform something here and here. So these patterns are really the basic pattern of game semantics. So this says that game semantics on filiform formulas. So the filiform formulas are the formulas with no tensor. So they are just negation of negation of negation of negation of negation of true. Okay, so they are very boring formulas. But the logic on these formulas is really captured by the fact that negation is adjoint to itself. And this may be seen here. If you count the number of proofs from the negation of A to the power 2p to the negation of A to the power 2q, and A is like for typically the unit. Okay? Well, they are just increasing functions from p to q. So where p is this totally ordered set on p elements. So this says that inside this universe of proofs, there is the category of augmented simplices. So this means that there is a lot of work on the combinatorics of simplices. And so proof theory may be seen in a way as an extension. Okay? And so we should produce a combinatorics of proofs in the same way. And here, of course, the reason why they are the same is that all the proofs are generated by the unit and the multiplication of the monad, the double negation monad. And so this is the unit, the proof that A implies not A, and the multiplication is the proof that for negation of A, so a lot of hesitation, imply a double negation of A. Okay? And all the proofs between filiform formulas are produced by these two proofs. And just to compare, this is the notation, the typical notation in proof theory, so sequent calculus. and there are the string diagrams here. So, I mean, on these very basic instances, it's clear that notation matters. Okay? So, in a way, it's easier to understand what happens on string diagrams than here. Okay? But it's not just, you know, about seeing things. It's about understanding them. And so, one important thing here is that we see proofs as generated, okay, by generators and relations. But on the other hand, we looked only at very specific proofs, which are filiform proofs. Okay, so the question then is, maybe I should jump this, it's fascinating, but okay. So we looked only at filiform formulas. And we want to understand, okay, what it means to add ingredients, logical ingredients to negation. So typically, what happens when we have negation and a tensor product? Okay? Are we able to understand exactly the generators of proofs? And it appears that we can. So, in this way. So, the first thing that happens when a tensor meets a negation is this, and this is a very well-recognized fact, that the double negation monad, the monad induced by the self-adjunction, is strong. And this means that it interacts with the tensor product in this way, that when you have a double negation of A tensor B, then you may transport it to a double negation of A tensor B. Okay? And you may think of this map as a typical proof. Okay? This should be a generator, if you like, of our proof theory. Okay? The question is it sufficient to construct all the proofs? And the answer is no. So when you have a tensor, a monoidal category, and a negation in it, this doesn't generate all the proofs, but nearly so. So in fact, you need a parametric strength. So parametric strength says this, so that, imagine that here x, so the x is the parameter. Imagine that x is the unit, then this is the same thing as before. So the double negation of A tensor B is the same as the double negation of A tensor B. But here I add an x here. Okay? And here there is a proof of this factor. And the proof is very special because it generates all the other proofs of the logic. And it's quite interesting to understand algebraically. And we will see that it may be seen as a kind of distributivity law between a monad and a comonad. And I will come back to this later on. But let's mention the fact that we had two-dimensional string diagrams for describing negation, but when we have negation and tensor, we need three-dimensional diagrams, because what happens here is that we are transporting the formula. So typically this formula here is the tensor product of the double negation of A and the double negation of B. So we transport this tree, if you like, into another tree here, which is the double negation of A tensor B. And to do this, we use three generators. The first one is the strength, so it transports a double negation here. The second one is the strength on B, okay? And then we use the co-unit of the adjunction. And this produces one of the two proofs, so there are two canonical proofs of this fact. Okay? And I will come back to it, because the fact that there are two proofs is very important when we think about the relationship between intuitionistic logic and classical logic. So in particular, maybe I don't know how much time I have, that's my problem. In fact.
You have 10 more minutes, and
okay.
then 10 minutes for questions.
Okay, so I will jump this, I will maybe jump this. I will just, since I'm on this topic now, so you mentioned star autonomous categories, okay? And the question is, okay, so given a dialogue category, so it's a category with a negation, but the negation is not involutive, how do we produce a star autonomous category. And the question, in fact, should be understood from a logical point of view, at the same time algebraic point of view. So, because it amounts to transporting, if you like, an intuitionistic logic, which is the logic of negation in the dialogue category, to a classical one, which is a logic of negation in a star autonomous category, okay, where negation is involutive. So how do you do this, usually? Well, there is in the Boolean algebras, whenever you have a Heyting algebra, you take the negated elements and you have a Boolean algebra. Okay? And this may be seen as a very nice algebraic account of the double negation translation by Gödel. Okay? But now if you do this with a dialogue category, you don't get the star autonomous category. Okay? Usually it won't work. On the other hand, it will work precisely when the monad, the double negation monad, is not just strong, it's commutative. And the reason is that when it is a commutative monad, so commutative means that the two canonical maps here are equal, okay? Which means that in a way you forget all about this story about double negation, but there is a canonical way, a unique way to do it, whereas in general there are two ways to do it. Okay, if you do this, well, if you have this, then the double negation monad in fact is involutive, and this amounts to these string diagrams here, which means that if you like, the flow of information is completely disrupted. Okay, so this means this is equal to this. So if you think about these string diagrams as describing a strategy, an interactive strategy, well, this strategy is then the same as this one. Okay? And in particular, all so if you remember, we had lots of proofs between our filiform formulas, and now there is just one. Okay? Because this is a very strong equality here. So it identifies all the various proofs. And this means, in a way, that in linear logic, there is no immediate account of dynamics, because negation is involutive. And in particular, and this was the main problem, when one wants to have a model of linear logic using games, one needs to impose this kind of equalities. Okay? And in other words, the proper logic of games, if you like, is not really linear logic, but linear logic when involution of negation is relaxed. Okay. And in general, you don't have these equalities, and so you don't get a star autonomous category by looking at the negated elements. So here, the negated elements, this is the same thing in this situation as the classic category of the monad. Okay. Okay. So, and maybe I should mention this, that I arrived to this conclusion by trying to develop a notion of games playing on concurrent or concurrent boards, if you like. So, situation where you can permute moves during so imagine that you are looking at plays up to deformation, so you may permute two moves. Okay? And this idea really came from the work with Samson when I was in Edinburgh. Okay? So it's a long story because it's quite a long time ago. Okay? But this means that very basic semantic problems about game semantics are in fact related to algebraic problems. So the question whether the double negation monad is strong only or also commutative. And if you look at the two strategies, the two canonical strategies in game semantics from here to here, they may be seen as this. So think about, so every move here, so there are 6 moves here on these games, is a negation. And so this means there are 2 ways to call, here there are 2 ways to order the inquiries on the 2 inputs. So the left and the right strategy to do the proof, and they may be seen in this kind of concurrent setting as the two borders, the two sides of this box. And the idea is that you have the two strategies here, and it's possible to mystify the audience. So it's possible to identify the two proofs in the category of games without the category collapsing to an order. Okay? And the reason is that all your audience are proofs, and as such they are technically called innocent. And innocence means essentially that they will not be able, they do not really care about the order of inquiries. You know, so if your opponent asks you a question in one order or the other, you don't really care. So this enables to identify the two proofs here and to obtain a negation which was associated monad is commutative, and thus a model of linear logic. But it's a lot of work. And so it's better to think that we should remove this hypothesis here. Okay? And really look at a situation where negation is not involutive. So now I have 5 minutes maybe, so I will speak about the first 2 words of my title. I will jump this, it's a pity, but okay. Maybe I should just mention that in fact there is a general principle that may be analyzed using 2 monads. So you see we are in a situation with an adjunction, and there is an interesting fact that whenever B is, say, an algebra, or even a lax algebra of a 2 monad, then the structure will be transported to A here. Okay? And this is exactly what happens in this situation with the par. So the par is the disjunction in linear logic. It's a strange animal. And if you relax the hypothesis that double negation is the identity, you construct something here which is a lax disjunction. So this means that you don't have anymore that so this is the notation of this thing. Okay. You don't have any map here between them. Okay. On the other hand, there is a map here. Okay. And this is important to us, computer scientists, because this is the type of a program with 3 inputs, and each of them of type A, B, and C. And the difficulty with linear logic is that this equality between the types doesn't happen in programs. Whereas this structure here is very natural. If you think about the interpretation of this type using continuation semantics. So the relaxation is also a way to connect logic to programming language semantics in a more natural way, I would say. And in order to do the connection properly, one should study 2-dimensional monad theory. Okay, and I will. Yes. And I should mention, because maybe it's interesting for few of us here, that it's possible to think of this generalization of a strong monad as in fact a distributivity law between monad, which is the original monad, and another structure, which is the tensor product of the monoidal category, but seen this time either as a monad or as a comonad. Okay? So this means that but in order to do this, one needs to extend the notion of monad and think in terms of parametric monads, or if you like, which are the same thing as lax algebras of this 2 functor this means that it's possible to, it's also an opportunity to organize a bit better the kind of foundations, not of physics, but of computer science and semantics. And I will just conclude with this, that I think is interesting to the audience. So I discussed a lot about dialogue categories and star autonomous categories and relation between them. And the idea is that negation, classical negation is involutive, whereas intuitionistic negation is not, but there is a good way to understand the relationship between them. And in fact, so as I mentioned at the very beginning of the talk, Day and Street noticed that a star autonomous category, so if you like classical negation, is the same thing essentially as a Frobenius algebra in a category, so the bicategory of modules, or profunctors. Okay? So, and from this they developed a general theory of quantum groupoids. And the idea is that when you take a groupoid, there is a map which transports an arrow to its inverse. Okay? And this map has exactly the same structure as classical negation. Okay? So, so then the idea is, okay, and classical negation is the same thing as a Frobenius algebra, so this works together, and which, so it's tempting to define, so the definition is a bit involved, but to define a quantum groupoid as some kind of monoidal adjunction between, let's say, a commodule of edges to a commodule of vertices. Okay, and there is this nice observation that we have a duality which is ambidextre. Okay, so this thing here is a Frobenius algebra, and here we should ask that it is a Frobenius algebra and that this structure preserves this. And this enables to transport the definition of groupoid, and the groupoid is exactly the same thing, but here you replace vector spaces by sets. Okay, so two vector spaces, and the intuition, okay, the intuition behind this is quite strong, I think, is that Hopf algebra, okay, should be understood as a group, okay, but transported from the category of sets, okay, because the linearization of a set is a strong monoidal functor, so it transports a group to a Hopf algebra. Okay. So here, if we think about groupoid, well, it is this strange animal, but in a category based on sets here. And so now we have a functor from sets to vector spaces, and it will transport our category to this, and our groupoid to this structure. Okay? So, so this means that the questions about classical negation versus intuitionistic negation have pervaded, the field of logic. So it's really a question about dualities. And the fact that the free, if you like, that after years of work, the intuitionistic situation, so the intuitionistic negation is meaningful for us computer scientists and logicians. Compels us to look at this algebraic situation in order to understand whether there is some kind of, intuitionistic variant of quantum algebra and whether it makes sense or not. Okay? So, one could think of this as a possible direction of relaxing the usual notion of cobordism and Frobenius algebras. So there is the dimensional thing, okay, so take n-dimensional cobordism, but here there is a kind of, additional option that I think is worth exploring. Thank you.
Any questions, comments? Jane?
Could you describe the connection between negation and Frobenius algebras? I didn't understand the...
Okay, I can. So there are several definitions of Frobenius algebra. Okay, so this is the kind
Several
of
equivalent ones. You mean?
typical one.
Yeah.
Okay, but there are more clever ones or more concise ones. And in fact, one of them is here. So this is an alternative definition. So here, so this is an alternative definition of a Frobenius algebra, if you like. So you ask that it's an algebra equipped with a form. And the form has the property that is called associative, which says that I'm stupid, I have all these things, but I don't... Ah, yes, it's here. So...
But I mean, your little negation there, shouldn't it be over on the right slightly rather than on the top?
Yeah, well, that's the point. It's adjoint to itself. So this means that it lives at the same time on the left or on the right. Because an adjunction is typically, you will have something like... Oh. Okay. So if it's adjoint to itself, you can put it on top.
Yeah, but it's just that it looks as though that's taking in two arguments and spitting out a set.
Yes, but you should think of it. That's the point, yes. And the point then is that, so if you rewrite it in the kind of algebraic way, this says this. Okay. So a Frobenius algebra may be defined as an algebra equipped with this in such a way that it defines a proper duality. So because it's possible, I mean, you see here.
So you need sort of,
It should be a part of a duality.
So you need sort of, there has to be a sort of non-degeneracy.
Yes, but the non-degeneracy really amounts to the fact that this may be complemented, if you like. So this is this may be thought as some kind of co-unit, and there should be a unit to the duality.
Don't you have to require that as well, or is that automatically?
No, you have to require it.
Yeah.
So this means that you have this and also the yes, indeed.
So I still don't see why that gives you negation. Maybe I don't really know what negation... I mean, I still don't see why you can say Frobenius algebras is the same as negation.
No, okay. So okay, let's admit that Frobenius algebra are presented in this way, okay, with some non-degeneracy hypothesis, okay. What I'm saying now is that, so this is the pattern in some category by category of modules, okay. So you're here, you have your object, your algebra. Now, you just take the definition, the kind of two-dimensional definition, okay, and you remove the underlying category, and instead you put the bicategory of modules, but on sets this time, so profunctors, okay, distributors. And then, so this equation here becomes this thing here. So it says that there are just as many maps from A tensor B to not C as maps from A to not B tensor C. Okay? And this captures really what is negation. I mean, of course, it's an intuitionistic negation, if you like.
So
okay? But the point is that in the situation, so the non-degeneracy that you mentioned, if you like, will force this to be an equivalence. So what I'm saying is, if you like, that one should, so if one starts from this definition, then going from a classical negation to an intuitionistic negation means to replace the self-duality equivalence that you have, because when you say that double negation is the identity up to isomorphism, then this means you are equivalent to the opposite category. And here, no, you want an adjunction instead. And so this is very much in the spirit of deformation of algebraic structure to see more. Okay, so when you deform it, you will see things appear. And in particular, these laws, so when you relax the notion of Frobenius algebra, these laws are not true anymore. There are coercions, there are maps between them which are not isomorphisms. And this means that you are doing, if you like, you are doing cobordism with negations inside. And I want to understand better what it means. And that's the point. Because, I mean, there is this story of, you know, games and proofs and logic behind to support the things. So in particular, maybe I should mention this. There are interesting factorization systems that, yes. So there is something very important, is that it's possible to factor every map in some ways. So this means that when you are in dialogue categories, so in an intuitionistic situation, you have more structure in a way than when you are in a star autonomous or classical negation. You see things appearing, which were not clear at all in a classical case. So now, since it's related to cobordism, it's interesting to understand what it means, whether it has some other kind of geometric reflections.
Right, well, so you think that Frobenius algebra is a role to play in game semantics?
Well, this is what, I mean, it's a very, it's a very striking fact that it says that Frobenius algebras have to do with logic in a very deep way. Because you should remember that Michael Barr wrote this book about star autonomous categories, but then it was really, people really started to work a lot on it when linear logic came around, and people understood that star autonomous categories were the categories underlying linear logic and these things. And it was 20 years ago, and a lot of work has been devoted to this. There were problems to understand the relationship with game semantics, because we could do game semantics for only fragments of linear logic, so it was a bit perplexing. And so now it's much clearer, I think, with this kind of relaxation of the logic. No, the point is that we were tempted to put the blame on the game semantics, but it was rather that we were asking too much of the logic. And so, in a way, you remember the very beginning of the talk, it's very interesting to look at logic in parts. So negation and tensor, and existential quantification, and all these things, and to understand how they are related really. And it's so algebraic in shape that, in fact, it's related to other problems, which are other abstractions of physical situations. And the connection was produced by Day and Street, and it's a very striking fact.
And can you give us an example of one of those things where the double negation is not that's not identity?
Yes. So typically, if you think about vector spaces, so if they are finite dimensional, it is. Otherwise, you don't know. Okay? So this means that a space is included in this bidual. Okay, this is a very simple situation. And in fact, so there is a kind of philosophy behind it, if you like, that we should try to understand every components of duality. And here it's clear that classical duality, if you like, forgets a lot about it. So it's interesting to decompose it. Yes, sorry.
One example I was thinking of as you spoke was of elementary toposes using a Cartesian structure and the contravariant power set function. So is that a...
Yes, indeed. So in every Cartesian closed category, every object will define so replace it. Define such a thing.
And we know that lots more structure comes out of just that.
Sure.
Quite an economical way.
Yes. So that's the point of I like to think of this practice as some kind of atomic attitude to logic. You take a small bit and then you analyze it entirely. And so you understand the generators, the relations, what it means, and everything. When it's done, you add something. And here, of course, if it's the two, okay, or the Boolean object, it will have a lot of more. Typically, this will simply already be a monad. You see, so, and there is a reason behind this, is that you have every object is equipped with some maps. So typically, there is the equality. I mean, the reason why you have a map from A to the power set of A is that there is equality. So there is a map from A times A to 2. So this is more. So then, you see, so this, the free theory of this is game semantics. Okay? Then if you add things to it, then wow, what happens to semantics is interesting.
Okay, we thank Paul and Ray again.